Okay, hello everyone. How are you? Good? Professor Mudlu cannot be here today, so I'm going to teach this thing, SIMD processors and GPUs, which is my favorite lecture. How was the exam yesterday? Was it okay? Good? Okay, we'll see when we grade it. Yeah, okay, so what's different today with respect to previous lectures? It's different the fact that we are not focusing today so much in memory, even though we would talk about memory. You know that most of the previous lectures have been around DRAM, how DRAM works, DRAM reliability, security, and so on. And now we are going to start, let's say, a new, at least today, we work with a new block of contents of the course, which is processing paradigms. And today we are going to talk about two processing paradigms that are very related, or at least one of them is based on the other one. GPUs are based on SIMD processors, and that's what we are going to talk about today. So first part of the lecture will be about SIMD processing, and here we will discuss, or we will introduce vector and array processors, and in the second part of the lecture we will talk about graphics processing units. I'm pretty sure that many of you must already be familiar with these two topics. Maybe if someone has already taken the computer, the design of digital circuits course with Professor Mudlu, you might have seen already these slides. But yeah, because probably it's not the case for everyone, I think it's good. And also, this lecture is going to be also like introductory of a possible later lecture that we will have about GPU and heterogeneous programming, which is a topic that is quite useful and also very much related with some of the research lines that we have in the group. So over the course of the lecture, please don't hesitate to stop to ask questions, and if we can have like some sort of discussion, that also could be really nice. Okay, so essentially what are SIMD processors and GPUs? Essentially what they are is parallel machines. They are data parallel machines. They are machines that are able to execute computation on multiple data instances at the same time. So what we exploit here is what is called the data parallelism. But as you will see, this is not the only thing that we're going to be able to execute, for example, in GPUs, where we can also have some sort of task parallelism. We will talk about that later. But in principle, this is what it is data parallelism, and especially, I mean, they will be especially good when this data parallelism is regular, okay? So before we start, it is good that we take a look, or we somehow review something that I'm pretty sure that you already know, is the Flynn taxonomy of computers. Mike Flynn in 1966 classified computing systems in four main categories based on how do they execute instructions to operate on data. The simplest of this category is SISD, is the first one, single instruction, single data. This is what we understand by a sequential machine, okay, or a scalar machine, where we operate one single instruction on one single data element. The next one is SIMD. Single instruction operates on multiple data elements. We have a lot of elements, maybe hundreds, thousands, or millions of elements, and the instruction that we want to execute on these individual elements is the same for all of them. So that's what we call the SIMD paradigm. In this paradigm, we have the two main types of processors that we will talk about in the first part of the lecture, are the array processors and the vector processors. Then we have multiple instructions operate on single data element. This is not something that you will find so frequently in real world machines, but there are some of these, like for at least similar ones, like for example systolic array processors, streaming processors, or you might have heard also about, I think Professor Mudu talked here about the Micron's automata processor, could be seen as some sort of MISD. And the last one is SIMD, multiple instructions operate on multiple data elements. We have multiple instruction streams. Examples of these, or let's say the most straightforward examples of these, are multiprocessors and multi-thread processors, like for example the multi-core processors that we have these days in every computer or even cell phones. Okay, where are we today? In this SIMD, right? Single instruction operates on multiple data elements. Let's talk about data parallelism. How are these SIMD processors going to exploit data parallelism? They are going to perform concurrent execution by executing the same operation on different pieces of data. This is what we call single instruction multiple data, and there are many examples of possible single instruction multiple data execution in real world applications. For example, the dot product of two vectors, right? When you're doing the dot product, what you do, first thing that you do is multiplying one element of one vector with another element of the other vector, or let's say element 0 of the first vector multiplies by element 0 of the second vector, element 1 by element 1, and so on, right? So we have data parallelism there because we have multiple data that we have to operate on, and it's SIMD because we can execute the same instruction on all these instances of data. Here, just very briefly, what's different with respect to data flow machines or data flow execution? It's different because in data parallelism, the concurrency arises from the fact that we need to perform the same computation on multiple data elements. In data flow machines, the concurrency arises from the fact that we can execute multiple different operations in parallel, and we say in a data-driven manner because these operations are only fired when the data is ready. Okay. And also the contrast with thread or control parallelism, which would be something similar to programming with multiple threads like P threads, OpenMP, and so on, which is what we usually do in multiprocessors or in multi-core machines. There we have different threads that can execute completely different programs, right? In SIMD, what we are doing is exploiting operation level parallelism on multiple data, and this can be seen as a form of instruction level parallelism, meaning that we have multiple instructions that can be executed in parallel. But it turns out that this instruction level parallelism, the instructions are always the same ones, right? It's the same instruction that is applied on multiple data elements. So in SIMD processing, single instruction operates on multiple data elements, and this is something when we actually run the computation, when we actually have this concurrent execution that we were saying in the previous slide, this is something that can happen in time or in space. We will typically have multiple processing elements, not always. You will see some examples later, but we will typically have multiple processing elements, and we have this time-space duality that differentiates between what we call the array processor and what we call the vector processor. In order to see this very clearly with a very clear example, we have the next slide, and here you can observe already the main differences between the array processor on the left hand side and the vector processor on the right side. As you can see, in this array processor we have 4 processing elements, and the 4 processing elements are exactly the same. The only thing that is different is that they have a different index, right, from processing element 0 to processing element 3. In the case of the vector processor, we have several processing elements as well, but these are specialized. They are not able to execute every instruction, as is the case in the processing elements of the array processor. Here, what we have is processing elements, each of which is specialized on a certain type of instruction. And you can already see that here we have one of them for load instructions, add instructions, multiply, and store. Okay, and how do we execute a program on these processing elements in the array or the vector processor? Okay, let's assume that this is our program, very simple one. What you see is that first thing that we do is a load instruction. So here we go to memory, to this array A, and we read some elements, in this case 4 elements, right, from A0 to A3. We read these 4 elements and we place them, we keep them in this vector register. Next, we operate on the vector register. We add 1 to every single element, to the 4 elements that we just loaded into the vector register. After that, we multiply by 2, and finally we store the result in the same array that we had in memory, right? How do we execute this on an array processor? So, because we have 4 elements, we want to read the 4 elements at the same time. So, first thing to do is this load instruction is executed on the 4 processing elements in the first cycle, or at least we issue the instruction in the first cycle. It might take more than 1 cycle to execute, right? But we can issue the 4 loads at the same time in the same cycle. When we are done with the load instruction, we schedule this add instruction, and because these processing elements are somehow flexible or general purpose, because they can execute many different instructions, so we are executing this add 0, 1, 2, and 3 using the same processing elements. And then we have the multiplication, and then we have the store operation. How do we do that in a vector processor? The first thing that we have to do is issue 1 load. This load 0 will load element 0 of array A. 1 cycle later, we can issue load 1, and if we already have the value that we have to read from memory, A0, then we can start operating on it, right? Let's assume that we can do all these instructions in one single cycle, right? So right after we get the value A0 from memory, we can start adding 1 in the corresponding processing element. And in the next cycle, load 2, add 1 and multiply 0, and then load 3, add 2, multiply 1, and store 0, and so on. Okay? So, observe the difference. In the case of the array processor, we have the same operation at the same time. In the case of the vector processor, we have different operations at the same time, in the same cycle. If we look at the space, recall the time-space duality that we were mentioning in the previous slide. If we talk about the space, then we have different operations in the same space, in the same processing element. In the case of the vector processor, we have the same operation on the same processing element. Okay? Okay, we were comparing before with data flow machines and with multi-thread machines. One more comparison that is worth doing, you might also be familiar with the VLIW paradigm, very long instruction words. This is sort of machines that held by a very wonderful compiler that is able to extract instruction level parallelism from the programs. They create a program where every single instruction is a very long instruction that actually has like multiple instructions in it, multiple instructions that are independent and can be issued at the same time. So they can be executed on the processing elements at the same time because they are independent, and we can exploit instruction level parallelism in this way. Why is this different from SIMD processing? Well, it's different. I think it must be clear that here We have multiple processing elements as well, but on each of them we are going to execute a different instruction that will be likely working on different data elements as well. While in a SIMD processor and a SIMD array processor, we have one single instruction, and this instruction is executed on the 4 elements, okay, operating on different data instances. Okay, so yeah, let's continue with vector processors. Vector processors, I mean, receive this name because they operate on vectors, right? And you know already what's a vector. You know that this is in principle, one-dimensional array of numbers. It can also be like 2-dimensional or 3-dimensional, etc. But in principle, we will only talk about one-dimensional arrays. Many scientific commercial programs use vectors. This is something that you already know, and here we have our first example operating on 2 vectors, A and B, and we are calculating the average of element-wise average of these vectors and storing the result in array C. So this program is like the typical vectorizable program that we want to execute on a SIMD processor. So here we have multiple instructions, so we have instructions that operate on vectors, not on scalars, and there are some basic requirements or basic things that we are going to find in a vector processor. These are first of all, we need to be able to load and store vectors, and for that what we use is these vector registers. Recall the example that we had before. We execute the load instruction, we have to go to memory. In that example we were reading 4 elements at a time, and when we read the 4 elements from memory, where do we put them? We have to put them in a register, right? So these registers are called vector registers, and each of them will contain multiple data instances or elements of the vectors. But these vectors, and so these vector registers have a certain length, right? So they will have the size that they have, right? For example, 50, and we can fit 50 elements in them, and this is what we call the vector length. Usually this vector length is going to be stored in a specific register, in a special register that will contain the vector length. And then there is another register that is important for the data access, for the memory access, is the vector stride. In the example that we saw before, or in this example as well, what you can see is that we always access consecutive elements, right? We would start from element 0 until element 49, and we are going to read them all. So here, what's the stride? Among consecutive accesses, the stride is 1, right? No matter, I mean, we are not talking about the vector length here, but assume that the vector length is 50, so we can read the 50 elements at the same time, and we could do that. But the stride among these elements is just 1. In some cases it won't be that way, right? In some cases we are going to have a strided access. We might be, for example, reading only even elements or only odd elements, right? And in that case our stride would be 2. So when we are writing a vector program, a vector processing program, and we need to access memory with a certain stride, we will have to enter that stride into this register. So, vector instruction performs an operation on each element in consecutive cycles. This is what we saw if we go back to the vector, this comparison here. We operate on different elements in different cycles. This is the case in vector processors, right? So that's what we have here. The good thing of doing that is that it is possible, I mean, because these execution units, these processing elements will be typically pipeline. The good thing of using them for vector processing is that they can be deeper pipelines. We can have more pipeline stages, and I mean, I'm pretty sure that you're familiar with pipelining, right? You might remember that in a pipeline we have multiple stages. The more things or the more computation that we have in each of the stages, the longer the cycle will be, right? Because we have more combinational components there, so we need more time to traverse them all. So the cycle duration of the machine depends on how many operations, how many things we have to do in each of these pipeline stages. That's what is called the critical path. This critical path in the pipeline is what defines what's the frequency that the machine can operate at, right? So if we have deeper pipelines, we can probably have less things to do in each of the pipeline stages, and this way we can have a higher frequency. I mean, that's more or less the reasoning. And why is that possible? Why is it possible to have deeper pipelines when we are executing vector instructions? It is possible because there are no intra-vector dependencies. Recall how these vector instructions are executed in the vector processor. It's we start the operation on every single element in consecutive cycles, because in each processing element we operate on the entire vector, and because the computation that we apply to the different vector elements is completely independent of each other. Whatever I do with element A0 or element B0 is independent of what I do with element A15, right? So there is no intra-vector dependencies. So that's what this means. And there is also no control flow within a vector. Recall in a conventional pipeline. In a conventional pipeline you execute load instructions, add instructions, multiply instructions, but you also execute branches, right? Because you want to have control flow in your program. And the problem with these branches is that sometimes you need to wait a few cycles until the branches are resolved, right? This is something that doesn't happen in a pipeline processor, and one of these pipeline processing elements, if we execute vector instructions. Why is that? Because there is no, the execution of the operation on element A1 doesn't depend at all on the execution of element A0. So that's what this means. We don't have this control flow within a vector, so there's never a need to, for example, stall the pipeline because we have to wait until a branch is resolved, or these kind of things that happen in conventional pipelines. And also, we were talking before about the strided accesses. Here, the stride is known, right? I was saying, if you want to access only the even elements of the array, you will have to enter in this stride register, you will have to enter number 2, so that the hardware knows that the accesses have a stride of 2, right? And because this is something that the hardware knows in advance, then the memory access can be very efficient, right? For example, it is possible to prefetch data. It might turn out that at this point in time I'm operating on elements 0 to 49. I'm only operating on 15 elements because the vector length is 50. But the size of the array is much larger, right? For example, 200. The thing is that if I know the stride, I know that I will be accessing all the elements that are a certain stride. For example, with stride 2, I could be reading vector 0 or array A0, 2, 4, 6. And while I'm operating on these ones, I can be accessing memory and, for example, bringing from memory, prefetching element A20, 22, 24, and so on. And this is something that is doable, that is possible, because we know in advance what's going to be the stride of the memory accesses. So that's why we can also have efficient memory access here as well. Okay, advantages. I mean, we are already talking about the advantages, okay, right? But let's summarize them here. There are no dependencies within a vector, so this allows pipelining and parallelization to work very well. So we can have deep pipelines because there are no dependencies. Each instruction generates a lot of work. Why is that good? Because I only need to read from memory one instruction to operate on, for example, 50 elements, right? So in a conventional sequential machine, you need to go to memory to read instructions for operating on every single data element. And in this case, we are just fetching one instruction from memory to operate on multiple data elements. So from that point of view, this is more efficient. Highly regular memory access patterns. It's what I was just mentioning. This can also have some benefits in terms of exploiting the memory bandwidth better. And no need to explicitly code loops. What does this mean? I mean, just recall this for loop that we have there from 0 to 49. There is a for loop there, right? So every time that we want to execute each of these instructions, that is computing the average of the elements of A and elements of B, we need to compute and then check a condition and then jump, right? So these are the branch or the control flow instructions. We don't need them here. We don't, in principle, when we are operating inside a vector, we don't need them, right? Because we are operating on the 50 elements at the same time. But there are also disadvantages, of course. Very easy to understand disadvantage is the fact that we need the parallelism to be regular. What happens if the parallelism is irregular? Can you use the SIMD machine? Well, maybe you can use it as well, but for sure it won't be so efficient. We are going to talk about this again later when we talk about GPUs, because in GPUs it's possible to execute irregular parallelism. It is possible to do it, right? But for sure it won't be so efficient. You cannot achieve the same throughput as if you are executing regular computation, but at least you can do. And then another disadvantage of these vector processors is that they're also typically they are difficult to program, and this is something that already Fisher in 1983 pointed out. You can read this extract from the paper. To program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. That's hard to do in first place and just as hard to change. So this means programming is difficult. Why is that? Because when we are writing a vectorized program, or even when we are writing a program for a GPU, we need to try to make things regular as much as possible, or at least make sure that things are going to be executed in a regular manner, or at least as much as possible. Okay, well, based on this challenging thing that we have here, programming SIMD processors, we might have our GPU heterogeneous programming lecture later, another day. We will probably take a look at this slide again by then. And another disadvantage is that the memory bandwidth can easily become a bottleneck, especially if memory and compute operation balance is not maintained. What does this mean? This means that SIMD processors can be very efficient, right? You can have multiple processing elements working in parallel, and they can be operating on many input elements at the same time. Also, in these vector processors, and as we have just discussed, we can have deeper pipelines. Because we can have deeper pipelines, it's likely that we can operate at a higher frequency. So what this means essentially is that we have a lot of compute power. We can execute operations very, very fast. I mean, let's say arithmetic operations, for example, very, very fast, right? But in order to be able to execute these instructions, we need to be able to gather data from memory very quickly as well, right? And this is why this is going to be typically the bandwidth here, because as you already know, because this is something that Professor Mundu has explained, and that's actually what has motivated all this research that we are doing in processing in memory. Accessing data from memory is much more costly than operating on this data, and this is something that for sure is clear in vector processors and in GPUs these days. Even though they are incorporating these new memory technologies, like for example HBM, they are still bound by the memory bandwidth. Okay. Actually, I mean, you can even compare what's the ratio between the number, so between the peak flops, the peak floating point operations that you can execute on a GPU these days with respect to the bandwidth that this GPU provides. And if you compare this to a GPU that was built 10 years ago, for example, you will see that this ratio is even worse. This means that in 10 years, GPUs have changed, have evolved a lot. They have much more compute throughput, they have much more bandwidth, but the distance between these two is larger now than it was 10 years ago. So the memory bottleneck problem exists, and it's even worse these days. Well, we were talking about this compute memory operation balance, but also the fact that we need to make sure that the access to memory, at least we do our part, let's say we do our share, is like let's try to make the memory access efficient by mapping data appropriately to the memory banks. We will talk about the memory banks right now. Okay, vector processing in more depth. Any questions so far? Is everything clear? Okay, good. So we have already talked about the vector registers. Each vector register is going to be able to hold n bit values. Okay, so this is one of our vector registers. As you can see, here we can store up to n elements, and the size of these elements is n bits. Okay. And we have, in this case, like 3 different vector registers. Then we also have the vector control registers. We have already talked about 2 of them, vector length and vector stride. But there is a third one, which is super important as well, is the vector mask. Vector length is actually the maximum vector length. In the previous example, I was saying, oh, let's assume that our vector length is 50. What does this mean? This means that we can be operating on 50 elements at the same time, right? So we can be executing like computation on 50 operands at the same time. But this vector length is the maximum vector length that, as you can guess, it's related to the hardware. It's related to the number of processing elements that we actually have in our system. What happens if instead, I mean, the maximum vector length is n, the maximum vector length is 50, but we only want to operate on 15 elements, not 50. What would we do? So what we have to do is, in our program, we will have to say that this vlen is equal 15, not equal 50. Okay? And then we have the, well, we talked before about the vector stride, and here we have the vector mask register. This is going to be very useful, especially when our computation is not so regular, right? So we were saying before, SIMD processors or vector processors are very good when the parallelism is regular and when we use all the vector lanes, when we use all the elements in the vector registers and we operate on them in parallel, right? But what happens if that is not the case? What happens if, for whatever reason, we don't want to apply the same computation, the same instruction on this element, but we want to do it on this one and this one and this one and this one? Well, in that case, we can use the vector mask. Essentially, the vector mask will contain a value, 0 or 1, depending on the fact that we want to operate or not on a particular element. Okay? For example, we say, okay, if the element is 0, we don't want to operate on it. If it's 0, the value of vector mask I will be 0, and then we don't do anything. So that's the reason why we need this vector mask. Anyway, we will see a better example later in a few slides. Okay, vector functional units. What's what we call the vector functional unit? Is the collection of functional units that operate on a vector, right? We already know that they can have a deep pipeline, which means that we can have a faster clock cycle, and we don't have to worry that much about control of the deep pipeline, because the vector, the operations inside the vector are independent. This is something that we have mentioned before. Let's assume that this is our pipeline. It's a pipeline with 6 stages. Recall what I was saying before. So think, for example, that these were conventional scalar pipeline, right? Like in the MIPS pipeline, that I'm pretty sure that you have studied. And it turns out that here, for example, we have to access memory, and the instruction after the load instruction that is accessing memory is dependent on this load instruction. So what would happen is that if we are going to memory to read something, and this takes a few cycles, let's say 100 cycles or so, the next instructions that are dependent on this one will have to be stalled, right, until the load is resolved, until we get the value from memory, and then we can use the subsequent instructions can use the value read from memory. This doesn't happen in vector computing. Why is that? In vector processing, why is that? Because we have, in this case, 2 input vector registers, V1 and V2. They contain multiple operands, and what we do in this pipeline is that we first start the computation for element 0 in these vector registers, then element 1, then element 2, and when we fill the entire pipeline, we would be operating on 6 different elements of these vector registers, but the computation on them is completely independent, so control of this pipeline is pretty simple, as you can see. Okay, one example of vector machine, pretty old one, is Cray1. You can take a look at that technical board or data sheet from 1978 if you want, and this is like a schematic of this the internal organization of this vector machine. As you can see here, we have vector units, but also scalar units. For example, here you can see scalar compute units, there are floating point units here, there are vector units there, and here we have scalar registers, and here we have vector registers. You can see up to 8 vector registers, right? So this is like our very first example of real world vector machine. Actually, we have a very similar one at CAB. You might have seen it, this Cray XMP28, which is this beautiful, these days is no longer a supercomputer, now it's a coach. You can sit here, it's pretty comfortable. And because if you really want to run some computation here, you better go and buy one Raspberry Pi. You will see there as well. They both have similar peak throughput. Yeah, 400 megaflops. So yeah, you can take a look at this. It's a really beautiful one. And here in the next slides, you have a little bit more information about the internal organization. This particular model has 4 CPUs, and inside each of the CPUs, you have what we have seen in the previous slide as well, like scalar functional units, floating point, vector functional units, and so on. A little bit more information about the different models of this Cray XMP, different number of CPUs, memory size, number of banks, etc. A few more details here about the functional units, address functional unit, scalar, vector, floating point, and about the system configuration here and the different models, like information about type of memory, storage units, etc. And this is the person who was responsible for these computers, right? Seymour Cray. This is so-called the father of supercomputers, and I really like this sentence. If you were plowing a field, which would you rather use? Two strong oxen or 1,024 chickens? And here you have them. So what would you use? Well, it will depend, right? It will depend on what you really have to do. It depends on, all these different processing paradigms. You will choose the one that, or in principle, you have to think about choosing the one that adapts better to your workload, right? The thing is that in the end, we cannot build the perfect machine for every single workload, and usually we'll have to, computer architects have to take many trade-offs and decide, okay, let's have something, like a few, let's say, vector units, for example, but let's also have some scalar units as well, because they are useful for many other workloads. And this is actually something that Cray already knew, and that's why, even though this Cray 1 was the first vector machine, this doesn't mean that it wasn't also the fastest scalar machine of its time. So not only a vector machine, but also the fastest scalar machine. Okay, and much of the success of this vector processing is based on the fact that we can access memory pretty efficiently. And why is that? Because we can use multiple banks in memory. In this particular machine, for example, 16 memory banks. And let's see what we mean about the memory banks and about accessing memory in an efficient manner for vector processors. So we already know that we need to load and store multiple elements at the same time, or more or less at the same time. We will see how we do it, because we want to operate on them, because we have multiple processing elements that can run in parallel. So that's why we need to read and write multiple elements at the same time from memory. We already know that these elements are separated from each other by a constant stride. For now, we are going to assume a stride equal to 1. And as you will see, what we are going to do is that we are going to be able to load elements in consecutive cycles, and such that we can start a load of one element per cycle. This is something that we are going to be able to do by using multiple banks inside memory. Okay, so so the question is also, how can you do that if the memory access, a single memory access, takes more than one cycle? Recall the very first example that we had for array and vector processors, and I told you, okay, let's assume for now that every memory access, every instruction, every operation here takes one single cycle. But unfortunately, that's not the truth, right? You know that processing elements are usually pretty fast. You can execute, for example, an addition or a multiplication in just a few cycles, but if you have to go to memory, you have to go to DRAM, then you start, talking about the order of magnitude of 100 or 200 cycles or something like that. So yeah, so that what we can do if our memory accesses take longer than one single cycle, what we have to do is bank the memory. So what we are going to do is take the whole memory and we are going to divide it in multiple pieces that we are going to call banks, and that's what is called the memory banking. In this example we have 16 banks. Instead of having one single monolithic big memory, what we do is that the whole memory capacity is divided in 16 banks in this case. As you can see, each of the banks have its own MDR and MAR. I would like to remind you what this means. This is memory data register, memory address register. So how do we typically operate on this? We have an address bus here. So what we do is from the CPU, we use the address bus to bring the address that we want to access in memory to this MIR, and this MIR is connected in this case to bank 0, and this allows us to take the contents of this address and put them here to the MDR, and then by using the data bus we are able to bring this to the CPU. So this is how each of the banks individually works, right? But now what we want to do is operate on the 16 banks in parallel at the same time. And how do we do that? Well, what we can do is that we can issue one request every cycle, and because reading or writing from or into each of these banks takes more than one cycle, we are able to start issuing requests to the multiple banks, and a few cycles later we will start getting the values that we want to read from memory, right? So in this particular case we can sustain up to 16 accesses in parallel, or n accesses in parallel if we have n banks. This is one more nice slide to show you how the address is generated. Think about something like this. Recall that we have a stride, right? We have a base address, which is going to be, let's say, the starting address of the array, and then the elements that we are going to be reading or writing are going to be defined by this stride. So we need some sort of address generator like this, and this is the address that we will place in each of these MAR. Okay? So the way that we calculate the next address is the previous address plus the stride, and this is just one example, right? If the stride is 1 and consecutive elements are interleaved across banks, and the number of banks is greater or equal than the bank latency, then we can sustain one element cycle throughput. You understand that? What does it mean? It means that here we have 16 banks, and we're going to be reading one element from each bank. Why is that? Because the stride is 1, and because the consecutive elements are stored in consecutive banks. That's what this if says. And the last part of the if says the number of banks is greater or equal to the bank latency. Why is that? Why is that important? Because we want to receive one element every cycle. So for example here, imagine that the number of cycles that we need to read one element from each of these banks is 11. If it's 11, we will have to wait 11 cycles to read element 0 from this bank 0, right? So, because we don't want to just simply wait, what we do is put in more banks next to this one. And during these 11 cycles, what we are doing is that in the first cycle we start the request or start the read in bank 0. In the next cycle we start the next read from bank 1, then from bank 2, then from bank 3, and so on. And in 11 cycles later, we are still, issuing requests to the rest of banks. 11 cycles later, we can start reading the element that we needed from bank 0. You see? Now imagine that instead of being 11 cycles is 32 cycles. Okay, what would happen? During the first 16 cycles we are issuing requests, but then after that we would have to wait 16 more cycles until we can actually get the first value from memory, right? So that's why if we want to really, you know, like have our memory dimension in a nice way, we want to have more banks than cycles we need to access memory. Okay? You had a question?
Data, but say the bank latency is like 5, then if not it will need 20 banks instead of, because we can pre-fetch then 4 data at a time from 4 different banks and we can just overlap the latency. So it should not it be like bank latency into number of processing.
You are asking if the bank latency is related to the number of processing elements that we have, or?
Number of banks should be greater than equal to banks.
Oh, the number of banks related to the number of processing elements. Yeah, I mean that might make sense. I mean, it will depend on the specific architecture. For example, if you are thinking about an array processor, in an array processor where you have let's say 16 processing elements and each of them can execute every instruction like addition, multiplication and so on. So you compute something using additions, and right after that the next instruction is a load, right? So yeah, in this case it could make sense to say, okay, if I have 16 processing elements, let's have 16 banks as well, and so that we can issue the request for all of them at the same time. Okay, that's, let's say, intuitive, but doesn't really need to be like that, you know, because you could have more banks or you could have less banks as well. But how efficient this is actually going to work will depend on how many cycles you really need to read from memory. Okay? We can maybe discuss later specific examples, and we will likely have questions in the homework where you will have to think about this dimensioning. Okay? Okay, let's take a look at a good example here. It's element-wise average, right? You remember that code that we have seen before from I equals 0 to 30 to 41. We are going to calculate the element-wise average of the elements of two arrays A and B, right? And we store the result in array C. So this is an example of a scalar code. Let's think about a sequential machine, a CPU for example, and in this CPU what we are going to run to compute that element-wise average that we have there is something like this. This would be like our assembly or our matching code, right? So take a look at what we have here. First thing is we load 50 in register R0. Why is that? Because we need to perform 50 iterations to compute over the 50 elements that each of the arrays have. Then we have the address of A and the address of B respectively in registers R1 and R2, and then the address of C in R3. Next thing that we have is load instruction to load here into R4 something that we are reading from memory, and in particular we are reading R1, which is A. And then we have here some sort of auto increment addressing. We do the same for R2, which in this case is array B, and now we add these two registers, the contents of these two registers, R4 and R5, store the result in R6, and then we shift right because we want to it's dividing by 2, right? And then the result in R7 is what we write into memory. We store into memory in whatever address is determined by this register 3. And finally, the only thing that we do here is we decrement, in this case register 0, and compare the value to 0, and if it's not 0, then we jump or branch and go here and start. And we do this like 50 times, right? So if you count how many dynamic instructions we have here after, like running the 50 iterations of this loop, this means 304 dynamic instructions. Okay? Now recall that we have to read these 304 dynamic instructions from memory. Hopefully not from the main memory, hopefully from the instruction cache, but we still have to fetch them from memory. Okay, the problem with this scalar code is that, it's quite inefficient, right? Why is that? Well, first of all, let's assume that first of all, let's think about a memory with one single bank. If we have a memory with one single bank and we compute how many cycles in total do we need to execute these 304 dynamic instructions, what we will have to do is adding up all these latencies that we have here. I didn't mention that, but here in this column what we have is the latency of each of these individual instructions. So for example, load instructions take 11 cycles. So the calculation in the next slide is say, okay, I have 50 iterations, so this is 11 plus 11 plus 4 plus 1 plus 11 plus 2 is the number of cycles from a single iteration, so then 50 of them, this is the total number of cycles here, 2004 cycles. This is in the case that we only have one single bank in memory, but because we don't want to be unfair, and we are going to compare to vector processors now, we are going to consider that this in-order processor, this very naive CPU, can already use like a memory with 16 banks. So what this means is that unless these two are mapped into the same bank, we're going to be able to read them at the same time. So let's assume that for example, A0 is in bank 0 and B0 is in bank 1. They are in different banks, so we can be reading both at the same time, right? So the good thing is that these 11 cycles can be overlapped, right? You already know that, right? So in the first cycle we issue this request, in the next cycle we issue this request, 11 cycles later we get this value, and 1 cycle later we get this value. So if we do that, then we can reduce the total number of cycles to 1504 cycles, okay? Okay. Yeah, here you have one. Why 16 banks? I already explained this, right? It depends on what's the memory latency. But now let's assume that, because all the computation that we had in that for loop to calculate the element-wise average is very regular, we can vectorize this loop, meaning that we can execute that computation on a SIMD processor or on a vector processor. So if we vectorize with this loop and we write this using vector instructions, we can have something like this. First thing to do is set vector length equal to 50. Okay, which is the number of iterations that we had in the loop. Next thing is vector stride equal to 1. Why is that? Because we are accessing all consecutive elements. And then vector load to read the 15 elements from array A, from vector A, and then another vector load to read the 50 elements from B, and then we add element plus element, all of them in these two vector registers, B0 and B1, then we shift right, and finally we store. So now, the latency of this is here. Each of the individual operations take exactly the same amount of cycles. But the good thing is that because we are using a vector machine, as soon as we issue one instruction, one load or one add or one shift right, in the next cycle we can start with the next operation. So that's why, for example, for this vector load, in the first cycle we issue the load for A0, and in the next cycle for A1, the next cycle A2, and so on. So after 11 plus VLAN 50 minus 1 cycles, we will have all the 15 elements read from memory. Make sense? So here, drastic reduction of the number of dynamic instructions is only 7, not 3 or 4. So recall what I was saying, we don't need to fetch so many instructions from memory. And now, for now, we are going to assume chaining. We will see what's chaining. Chaining means that we can, like forward data from one vector unit to another, from one vector processing element to another vector processing element. For now, we ignore this possibility. So we assume that we cannot start the execution of an instruction until the entire input operand vector register is ready. We consider that we have one memory port, meaning that we have one port per bank, so we can be only, so if we are using one memory bank, we can only be reading or writing one element at a time. And we have 16 banks, and the mapping that we assume is this one, is word interleaved, meaning that consecutive words, consecutive elements go to consecutive banks. And now we can see this timeline, how this code that we have here is executed, right? I already mentioned this, but yeah, so these two is just one single cycle, is stored in the vector length register and the vector stride register, and right after that we have the vector load. So in the first cycle we issue the request for element 0, one cycle later the issue for the request for element 1, element 2, and so on. After 11 cycles, because the latency of a memory access is 11, after 11 cycles we have A0. One cycle later A1, one cycle later A2. So in total, after 11 plus 49 cycles, we have this vector load executed. Now observe, we have one single memory port, so we can only start the next vector load when this first one is completely done. And again, it's exactly the same. 11 cycles to read from memory B0, and then one cycle later we will have the remaining 49 elements of vector B, for array B. And then we start the addition. Again, for the first addition we need 4 cycles, and then we will be obtaining the addition results in the next 49 cycles for shift and for store. So this in total is 285 cycles, which is already a strong reduction with respect. It's like 5 times faster or so than the thing for the sequential machine, right? Now let's assume that we can use vector chaining, which essentially means data forwarding. Essentially means that if we are reading these elements from A and from B, observe that as soon as we get here B0, we could start this addition, right? Why is that? Because we read A0 from memory in this point, and B0 from memory in this point. So right here we can already start the addition of A0 and B0, and this is actually something that makes a lot of sense, right? Why is that? Because we not only have load and store units in our system, we also have addition units, we have multiplication units, and maybe many more, right? So it doesn't really make sense to say, oh, okay, you can start the computation of the addition here, but let's wait until here. So during all this time, we could be using this addition unit, but we are not doing it, right? So we are wasting the resources. So vector chaining makes a lot of sense, and that's essentially what it is about, right? It's like, okay, I obtain a partial result from the load unit, and partial result meaning, you know what, one of these individual elements. So as soon as I get it, I can feed it into the multiply machine, in the multiply unit, for example, here, and as soon as I obtain the result of this multiplication, I can change the result and send it to the, or forward it to the addition unit, right? So this is chaining. So if we apply chaining to our element-wise average program, what we could do is exactly what I was telling you. Right after obtaining from memory B0, we can start the computation of the addition for A0 plus B0, right? And as soon as we have this addition, A0 plus B0, so we can start the shift right. Right? So observe that we are chaining from here to here, from here to here, and there's no chaining here simply because we have to wait for the store until the two loads have finished. And why is that? Okay, this is 182 cycles, so like 100 cycles less than the previous implementation. But still we have some problems here, and the problems is that we cannot parallelize memory accesses. But you see that these two vector loads cannot be pipeline, cannot be in parallel, and this vector store is exactly the same, right? We have to wait in order to start the vector store. We have to wait until the second vector load is completely finished, right? But observe that we could have started the store here, right? Because here is where we have already A0 plus B0 divided by 2. So we have it here, and we still have to wait a few cycles. And the reason why this happens is because we have one single port in each memory bank. So possibility here is to of course, at the expense of having a more expensive hardware, we could have 2 load ports and 1 store port in each bank. So if that's the case, this means that, for example, we have 2 load ports, so this means that we can be reading 2 elements from 2 different arrays that are mapped to the same bank, right? So we could be reading at the same time A0 and B0, assuming that they both are placed into the same bank, in bank 0, for example, right? So this is what we have here. We would only need to wait 1 cycle. Why is that? Because the address bus and the data bus is shared, right? But right after this cycle, we can start the vector load for B. And for the store operation, because the store port is also independent of the load ports, we can also start the store operation right here. We don't have to wait until this second vector load is done. So in total, like 19 times faster than the sequential machine. So it's quite good. Okay, questions? Yes? You mean
not just after the first one, after like every access you can't there's just one address at one time.
Yes.
So why is there a latency after the first one and not after the rest of these?
You mean this? The thing is that you generate one address every cycle. That's clear, right? So what you have here is that in the first, let's say cycle 0 or cycle 1, you generate the address for the first memory access, and 1 cycle later you have the address for the next memory access.
You're generating addresses for A and B.
Oh, you are generating addresses for A and B. Yeah, that's the thing, right? We have 2 load ports. So now you can assume that you can generate the addresses at the same time.
Then why do we have it in this?
Because of the data bus and the address bus. I mean, this. Okay. Also take into account that this is a simplification, right? So we don't go into all the details how this is let's say an abstraction of how this really operates. But if you check let me go back to the slide. It's here, right? This slide. So what you can assume is that this address bus is shared. So yeah, you might even have like several ports here, but still for moving the address from the CPU to the individual banks, you need to share this. You can assume that this is why you have to wait 1 cycle. But as I said, this is simplified. It's an abstraction. That's because that's what we have to do to explain the concepts, right? But that's more or less like that. Okay. Yeah, so next thing, what if the number of data elements is greater than the number of elements in a vector register? Okay, that's an important question. Why is that? Because, I mean, in the previous example, we were assuming that vector length was 50 and we have 50 processing elements there, or somehow, I mean, we can be operating on our vector registers at least can hold these 50 elements at the same time. But that won't be always the case, right? What happens if our vector length is 16? Or, for example, in this example, what happens if our vector length is 64? Meaning that every vector register can only hold 64 different values, right? But now, instead of operating on an array or a vector of 64 elements, we operate on 527 elements. So what do we need to do? In this particular case, we will first set the vector length register to the maximum possible, which is 64, and we carry out, like in this particular case, 8 iterations where the vector length is 64. So after the 8 iterations, we could have operated on 512 elements. But then we have 50 more elements, right? Because we have 527 in total. So what we would need to do is changing the content of the vector length register to 15 and then operate on the 15 elements. Okay? Yeah, so this is called vector strip mining, and the name is coming from surface mining or strip mining, which essentially is a mining technique that consists of getting rid of the bullshit that you don't need and simply take what you really want, like the gold or silver or whatever, right? So in our case, in the case of the vector registers, the goal is the data that you are really going to operate on, and the shitty part is this tail that you don't really need in the vector, right? Okay. Next question is, what if vector data is not stored in a striped fashion in memory? So this is interesting, right? Because as of now we were saying, oh, let's consider that the stride is 1, meaning that we are going to read all consecutive elements of the 2 input arrays or the 2 input vectors. Or now let's consider that the stride is 2 and we are reading A0, A2, A4 and so on. And this is fine, and actually we have already talked about the efficient memory access that we can have. We can prefetch data because we know what's the next data element that is going to be needed and so on. But unfortunately this is not going to be always the case, right? In some cases we will need to have irregular memory accesses, and for example you can think about a sparse matrix computation. We had the other day Konstantinos, right, presenting his work where he figured out ways, mechanisms, techniques to improve the operation on sparse matrices or vectors. So this is something that also applies here, right? If we are operating on dense matrices, then that's perfect, because the accesses for sure are going to be regular. We will actually see an example soon. But if we are operating on sparse matrices, then it's not only going to be like that. You might even remember that Konstantinos was talking about indirect address accesses, right? He talked about the CSR compression format, and he said, oh, you're going to have indirect memory accesses. So if you have to operate on sparse matrices or sparse data structures, you will likely have memory accesses like this one, where you first need to read one array D, and this array D contains the address that you need to read from array C, right? So the problem here is that the accesses to memory are not anymore regular, so they are probably going to be costlier. Yeah, but anyway, SIMD machines, SIMD processors usually have this sort of load indirect that can, starting from a base address, in this case RC is the base address, contains the base address of array C, and having some indices stored in this case vector D, which is something that we just read with the previous instruction. So we can generate the addresses from these two, from the base address plus the index inside the array C, and then go to memory and read some values and store them in vector C in this case. This is what is called a gather instruction. Why is that? Because we are gathering data from memory and we are putting these data elements inside a vector register. And the opposite operation is called the scatter operation, right? And here you have an example of that. This is the data that we need to store for elements, and these are the addresses in array C, for example, or the indices in array C where we have to store these values. So this is what we are going to store in memory. Okay, so this is, for example, this 314 goes to index 0, this 6.5 goes to index 2, and so on. And here we talk about a scatter operation, a scatter access, right? So we have the values that we need to store in a register, and then we scatter them across the whole memory, or the whole memory space occupied by the output array. Okay, yeah, so as you can guess also, I mean, is this more or less efficient than regular accesses? Well, it depends on the actual implementation, but as you can guess, this is typically going to be less efficient, right? And let me just give you an example. So these elements might be in different cache lines, right? And you know that memory is accessed at the granularity of a cache line. So what happens if our cache line size is 4, for example? I mean 4 elements, right? So these 4 are in one cache line, these 4 are in another cache line. And now in the same vector store, we are writing these 4 elements, and these 4 elements are scattered across 2 cache lines, meaning that we need to write into 2 cache lines. If we are reading, it's exactly the same, so we are reducing our throughput by half, right? Okay. Okay, next thing is conditional operations in a loop, and this is where we need to talk again about mask operations. We already mentioned that before, but now we are going to see a more concrete example. Recall that we have this vmask register, which is a bit mask that determines which data element should be acted upon or not. In summary, this vector mask is a register, and this register contains as many bits as our vector length. So we have 1 bit per vector for element inside the vector array. And if the value of the vector mask, of the value of this bit is 1, we want to execute the operation. If it's not, then we don't want to do that, right? And this is very useful whenever we have conditional operations. So for example here, we only want to perform this computation in case that AI is not 0. So what we do here is we first read a few elements from vector array A, from array B, and now we compare all the elements that we have in V0, we compare them to 0. If they are 0, then the result of this comparison is 0, so that's what we will have in the corresponding bit in the bit mask, in the vector mask. If these two are different, then the result is 1, and this 1 is the corresponding bit in the vector mask. And then the next operations are going to be conditioned or predicated to the contents of this vector mask. So for each of the elements in V0 and V1, these two vector registers, we will only execute this multiplication if the corresponding bit in the vector mask is 1. Okay? And this is how we can implement conditional execution in a vector machine. Right? So now, the good thing of doing this is that we can exploit irregular parallelism, right, by using this. So for example here, I don't know, we have n elements and maybe half of these elements are equal to 0 and the other half are not, right? So we need to operate on only n over 2 elements. So we still have parallelism, irregular parallelism, because we are not applying the same computation on the same elements. Good thing is that we can really use the machine. Bad thing is that we are not using all the lanes, right? All the vector length. We are only using half of it. Okay. As I said, this is what is called the predicated execution. So the execution is predicated on a mask bit. Okay. Yeah, another example with masking. Yeah, you have a different example here. If AI is greater or equal than BI, then you do this, you write A into C. If not, you write B into C. So how would we program this? So first thing to do is comparing A and B, comparing the elements in A and B to get the V mask. After that, we store into C those elements of A for which the mask is equal to 1. Then we complement the vector mask so that now the elements, so yeah, we are complementing it, that's clear. So now we store only those elements of B into C, those elements of B for which the mask is now equal to 1, right? So here you have the first, the example, the original value, the first value of the vector mask. If we compare A to B, A0 is not greater or equal than B0, so that's why this is 0. These two are equal, that's why this is 1. Okay. Yeah, and now just to finish with these mask vector instructions. So we would typically do something like this, right? So this is our vector pipeline, and we start computing on C0. I mean, we start calculating C0, C1, C2, and so on. So C0 is whatever A0 plus B0, for example. C1 is A1 plus B1, and so on. And for each of these operations, the mask has a value, 0 or 1. And so observe that all the computations, all the operations go through the pipeline, and only when we have the actual value, we check the vector mask and we decide if we write or not. So in this particular case, for C0, the mask is 0, so we don't enable the writing. It's kind of wasting cycles, right? So because that's the case, it's better to use this, or might be better to use this density time implementation. In the density time implementation, what we do is that we don't start the computation for some particular elements if the mask is 0. So this is why you can see that we are only issuing the computation for element 1, element 4, 5, and 7, and that's what we have here in the pipeline, right? So which one is better, and what are the trade-offs? So in principle, this is more efficient, right? The problem with this one is that we need to scan the mask before we start. So we are already adding some overhead before we actually start, right? So this makes the hardware more complicated, more expensive, but the good thing is that it will be more efficient. Okay? Okay, something similar to this is what current GPUs do to be able to execute irregular computations. So when we don't have all the same operation on all the elements of the vector, then that's what we have to do. I don't know if okay, I might be doing something wrong with this. Yeah, maybe we are going to have a break soon, so we can check. Okay. Okay, do you want to have a break now? Yes? Okay, let's have a break for 10 minutes. Is that fine? Okay, I think it's time to continue. Okay, so we were here, some issues, Stripe and banking. This is something that I might have mentioned already, but now we are going to discuss a little bit more, is what should be the relation between the Stripe that we have in the memory accesses and the number of banks, or and the banking. Well, we want them to be prime relative or relative prime. What does it mean? This means that the stride itself, this number, is prime relative to the number of banks. If that's not the case, then we will have bank conflicts. And let me give you an example. Let's think about matrices, right? You know that there are two possible ways that, well, at least two possible ways that we can map a matrix into memory. Memory is a linear array. Addresses are linear, right? And matrices are not linear. They are two-dimensional. So how do we store the rows and the columns of the matrix into this linear memory? There are two possibilities, at least. First possibility is we store all the elements of row 0, then all the elements of row 1, all the elements of row 2, and so on. And the other possibility is all the elements of column 0, all the elements of column 1, and so on. Okay? Well, let's assume that it's row major, which actually is the most typical one in programming languages like C, for example. Let's assume that we have these two matrices, A and B, and we want to multiply them. As you can see, this matrix A is 4 times 6, and this matrix B is 6 times 10. So we can multiply here, and to perform the multiplication, what we do is the dot product of a row of A and a column of B. Both are stored in the same memory, in the same system. So both are stored in row major order. This means that in memory they are stored like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And in this case it's 0 up to 9, and after 9 we have 10, and after 19, 20, and so on. Okay, so this is how they are mapped in memory. So how they are stored in memory. But now our memory is multi-bank. It has multiple banks. So I don't know how many banks for now, but let's assume that the interleaving is at the granularity of a word, meaning that A0 is in bank 0, A1 is in bank 1, A2 is in bank 2, and in this case B0 is in bank 0, B1 is in bank 1. And what happens with B10? Is it in bank 10? Well, if we have 10 banks, it will be in bank 10. I mean, if we have 11 banks, it will be in bank 10, right? But if we have 8 banks, for example, where is this element 0? It will be in bank 3, right? Okay, so this is how they are going to be mapped. And now what's the problem here? Because as long as we access consecutive addresses, perfectly fine, right? If we have a vector load that reads these 6 elements of the first row, row 0 of A, then they are going to be in consecutive banks, so we can read them, the 6 of them, at the same time. And if we do the same for B, it's perfectly fine as well. But what happens if we want to perform the dot product of this row and this column, and these guys are not in consecutive banks? then it will depend on what's the relation between the stride, which in this case is 10, as you see, and the number of banks. So if the total number of banks, let's say, is 10, then we are probably if the total number of banks is 10, we are perfectly fine for these 6 elements, right? Because from A0 to A5 they are going to be mapped into or stored into consecutive banks. But what happens with these ones? We have only 10 banks, right? So if we have 10 banks, it turns out that elements 0, 10, 20, 30 and so on are all mapped into the same bank, in bank 0. And the problem with that is that we cannot perform the accesses in parallel, concurrently. But we will have to wait. In order to read B10, we will have to wait until the access to B0 is completely finished. Right? Are we always going to have this sort of problem? We will always have this problem as long as the stride and the number of banks are not relatively prime. Right? So if the number of banks that we have is 16, for example, if it's 16, then that's fine. We have enough banks to be able to access B0 and B10 at the same time. And maybe B20 also maps to a different bank. But at some point, there will be some stride that will be a multiple of 16. And this means that we are not going to be able to access these two in parallel. Okay. Yeah, so this is essentially what this slide is about, and what we are doing here is describing what bank conflicts are. So bank conflicts are going to happen anytime that we want to access at the same time 2 data elements that are mapped into the same bank, because we can only sustain 1 access per bank in principle. Of course, it depends on how many ports we have, right? But for now, let's assume that we can have only 1 port per bank. Okay, is there any way of minimizing the potential bank conflicts? For sure we will have bank conflicts when accessing in a conventional machine. For sure we will have bank conflicts when accessing this matrix B. Is there any way of minimizing these banks? Yeah, there are possible ways. First way is more banks. Okay, that should work, but for sure it's more expensive. It's not a very good idea. Another possibility is to have a better data layout to match the access pattern. We can play different tricks, and actually if we have a chance to have a GPU programming lecture, I will give you at least one way of reducing the number of bank conflicts when programming GPUs. One possibility, let me very briefly mention what I mean. One possibility is to add some padding. Padding means that we are adding some, scattering some memory positions that we are not really using. For example, here, instead of having a matrix of 6 times 10, what we could do is reserve a little bit more space for this matrix, such that instead of having this and assuming that we have 10 banks, remember that was the original example here. Instead of having this guy here, we would write this guy here in the next position, and the position here, this memory address will be empty. So this is padding. So what we are doing is inserting some memory positions that we are not really using to store the actual values, such that we are able to shift these values, in this case to the right, to the next bank, and this way we would be avoiding the bank conflict. Anyway, that's one possibility. We will talk about that one probably in more detail in a later lecture. And then another possibility is to do a better mapping of address to bank. And for example, a randomized mapping. There are, for example, hash functions that you can use. Observe that here the way that you obtain in a naive example like this one, the way that you obtain what's the bank where one particular address is mapped to is just by looking at the least significant bits of the address, right? So if you are element 0, element 1, element 2 are mapped to bank 0, bank 1, bank 2, and so on. But we could randomize this in some way and say, okay, element 0 is going to be in bank 0, but element 1 is going to be in bank 7, and element 7 is going to be in bank 1. Why not? We can do that, right? And we can do that using hash functions. And this is something that was proposed in first time in this paper by Bob Brown in 1991. Pseudo randomly interleaved memory. It might be good, but I mean, it also has its own drawbacks, right? Because if you, I mean, for example, from the programmer's perspective, if you know how the data is mapped into the different banks, you can reason about that. But if you don't know what the hardware is actually doing, then it's much more difficult, right? If there is a hash function in between that you don't know exactly where is mapping a particular address that you're working with, then it might be more difficult for a programmer to reason about all of this. Okay, yeah, so we are already finishing this first part about array and vector processors. We have seen the difference between these two, data parallelism in time and or in space, and GPUs are a prime example, and we are going to talk about GPUs because GPUs, as you will see, have characteristics of things of or things of both paradigms, and not only about array and vector processors, but also about fine-grained multi-threading machines. We will also talk about that. Okay. One more thing is how to achieve this concurrent execution. With SIMD processors, we operate on multiple data elements at the same time by using one single instruction. But after saying that, we have seen how a vector processor works. And in a vector processor, we have seen that there are some specialized units, and each of them computes, performs the load, the addition, the multiplication, and so on. And we said also that these are like pipelines, so when we need to, for example, execute one addition of element A0 plus B0, in reality what we are doing is using this addition unit in a pipeline manner, right? So we are not really operating at the same time, right? But conceptually it's at the same time for sure. But that would be in the case that we only have one single functional unit. It might turn out that we have more than one functional unit, something like this. We could have 4 addition units, but we don't operate on only 4 elements. We can operate on, for example, 28 elements. So the way that we are going to schedule the computation here is by taking advantage of both time and space, right? So observe that in the very first cycle we can issue the addition for calculating C0, 1, 2, 3. In the next cycle for 4, 5, 6, 7, and so on. So this way, in the end, the program is exactly the same. It's V at A plus V, store the result in C. The way that we really execute this on the hardware depends on the hardware. If we have one single functional unit, it will be something like this. If we have multiple, it can be something like this. GPUs these days are more similar to this thing, as we will see. And each of these functional units are somehow arranged in this this way. So when we talk about a functional unit, here the functional unit would be these 4 pipelines, because the 4 of them are for the same type of instruction, for example addition, or for example multiplication. And then each of these columns that we have here is called a lane. It's called a vector lane. And observe that in this vector lane, what we have is registers, right? These are the elements. For example, element 0 and element 4 are going to be here. Here we have element 1 and element 5. Here we have element 2 and element 6. And this might be, for example, the multiplication unit, that one is the addition unit, and whenever we need to use either this or that, we would be going to this part of the register file. As you can see, the entire register file is partitioned, and part of the registers in the register file are assigned to each of the lanes. So whenever we need to use this, we will go to these registers, we will grab the corresponding elements, and we will start operating on them. But from the point of view of the vector register as we have defined it in the beginning of the lecture, the vector register would be the entire thing. Element 0 of vector register is here, element 1 of vector register is here, element 2 of the vector register is here. I hope that is clear. Okay, how do we schedule the computation in a hardware similar to this one? How do we schedule computation? We would be doing something like this. For example, here we have 32 elements in each vector register, but we only have 8 lanes. Okay, so this means that we can only start the computation for 8 operations, not for the 32 at the same time. So, for example, if we have a load unit and we want to load 32 elements from memory, first thing to do is starting the load for 8 of these elements, and in the cycle, the next cycle, for the next 8 elements, and in the next cycle for the next 8 elements. And that's what we are going to do for all these units. For example, the multiply unit. How many lanes do we have? We only have 8 lanes. We only have 8 lanes. But each of these functional units that we have there are pipeline. So every cycle we can start the multiplication for 8 elements. And in the next cycle for the next 8 elements. Right? Okay. We will see this slide again later. Yeah, as you can see here, in one single cycle, for example, this one, we are operating on, we are performing 24 operations. We are operating on 24 input operands. Okay, yeah, to do that, we need to vectorize our code. I mean, in principle, we were saying, oh, vectorizing code, writing vector code is very it's difficult, right? And because it's difficult, compilers have been trying to do this automatically for a long time. So, what a compiler needs to do if we want to vectorize a code automatically is to do some loop dependence analysis. And the compiler would be able to vectorize a loop, for example, the loop that we have there on the top of the slide, we'll be able to vectorize it if there are no loop carry dependencies, meaning that this iteration 2 is completely independent of iteration 1. And if that's the case, then we can generate vector code and we can perform these loads and these loads and these additions and these store operations at the same time, you know, in a SIMD fashion. Yeah, this will be particularly possible when we have regular data level parallelism. If it's not regular, or if we have loop carry dependencies, these kind of things, then the automatic vectorization won't be possible or won't be that easy. And in the end, we are always going to need to have the possibility of executing scalar operations. Recall what I was saying before about the Cray one. Even though it was a very good vector machine, it was also the fastest scalar machine at its time. Okay, and we are already done. Well, there are some examples in real systems of SIMD operations, and what we are going to do next is very briefly talk about some of these examples, or in particular one of these examples, which are the MMX instructions that were introduced in the 90s in Intel machines. So essentially the idea here is to make use of the registers that are already available in the system, in the x86 architecture, make also use of the functional units that there are already in that computer, and what we are going to do is using them to operate on, let's say, subwords. So if these are 32 bits, and these 32 bits originally were this register S0, what we can do is dividing this register into 4 chunks of 8 bits each, and in each of these 8 bits, groups of 8 bits or bytes, what we are going to do is storing different operands, in this case elements A3 or A0 to A3, and in the other 32-bit register we store elements B0 to B3, and now we can do a pack at 8, which means it's packed because the 4 elements are packed into the same register, is 8 because we are operating on 8-bit elements, and is the addition, right? Because we are doing this plus this, and the result is stored in these bits of the register S2. So that's what MMX instructions do. They use the registers that were already in the system, 64-bit registers, and in a 64-bit register you can either store one 64-bit element or 2 32-bit elements or 4 16-bit elements, and so on. And later what you can do is say, okay, now I'm going to execute one packed at 8 or one packed at 16, and depending what's the size of the input, we would be using one of these instructions. You can take a look at the paper as well. It might be required reading. I don't know that yet. This is that we will decide that later. And here you have a very simple example. Actually, I think that you can take a look at yourself about this at this example. I mean, these MMX instructions were included or were started in the 90s in these Intel CPUs, because in the 90s many multimedia applications started to be very, very popular. Same as these days we have many, for example, AI applications. And we start to incorporate all these applications in our computing systems. In the 90s, something similar happened to multimedia applications, and that's why Intel engineers thought, okay, it might be a good idea to incorporate in our ISA specific instructions that can operate on multimedia data, right? And that's what essentially MMX means, is multimedia execution. So that's where the acronym is coming from. In the example here, as you will see, that actually the example is in the paper as well. What you will see is a very simple way of doing image overlaying, which essentially is like like in when you watch in the TV the weather forecast, you see the forecast woman there, and at the back you will see the map of Zürich or Switzerland or wherever. So what they really have is a chroma, and later in the post-processing they replace all the pixels that are green or blue or whatever, they replace them with the actual, in this case is this kind of blossom background, but in the case of the weather forecast it will be like the the map or whatever. So essentially what this computation does is going one by one through each of these pixels and say, okay, if the pixel is blue, this means that it belongs to the background, and if it's blue, what I'm going to do is replacing in the output image, I'm going to replace that pixel with the pixel from the map or the pixel from this blossom background. And if it's not blue, it's because it's a woman, so if it's a woman, then I simply copy the value of the pixel to the output. And that's something that can be done in a SIMD machine, right? Why is that? Because the computation that we need to do here is exactly the same one for every single bit. And yeah, you can take a look at this by yourself. You will see that first it's a kind of mask generated, and then by using this mask we are able to remove the pixels from the background and replace them with the actual map or blossom background or whatever you want to put in the background. Okay, so this is the MMX extensions to from Intel machines, and now we are going to start with the GPUs. First thing here is GPUs are, I already mentioned that, they are a combination of vector processors, array processors, plus fine-grained multithreading. Very quickly remind you what fine-grained multithreading means. You probably used to, to see a pipeline like this, right? This can be a pipeline. Observe that here you have instruction fetch, and here you have an instruction register, and then you have some control logic that reads this instruction and generates some signals or some micro operations to, to tell all these, the rest of the components, you need to perform an addition, or you need to store this in memory, and so on, right? And here we have a register file where we store the values, the contents that we are operating on, and after that we have an ALU, and after that we have the memory access, and so on, right? So each of these stages is typically in a different pipeline stage, right? And within these stages, what we have are pipeline registers. I mean, between these stages. So if you think about very simple in order CPU, what we are going to have in each of these pipeline stages are different instructions that are at every point in time, at every cycle, they are in a different phase of their execution. You are, for every instruction, you are either fetching it from memory, or either decoding it, or either using the ALU, and so on. So in the pipeline we are able to achieve some sort of parallelism, because if we have instruction level parallelism, we can start the execution of an instruction before the previous instruction has committed, has completely finished its execution, right? But the problem with one of these pipelines is that there are instructions that are dependent on each other. Recall that we mentioned that in the beginning of the lecture. For example, if you have a load, if you have an access to memory, when you reach to this stage of the memory access, if it turns out that the data is not in the cache, then you need to go to DRAM, and this takes much longer, right? And because this stage takes much longer, if the instruction that you have after that, it's, for example, an addition that needs to use the data that you read from memory, then you will have to stop. You will have to wait until you bring the data from memory, right? And that's a problem that we have in one of these simple pipelines. So one thing that we could do is say, okay, because these days we have a lot of parallel programs, we want to have a machine that is able to run multiple threads at the same time. Maybe these threads belong to the same application or not. Maybe they are simply different processes. In this example, for example, we have 4. So if we have 4 threads and we interleave the execution of instructions coming from these 4 threads into this pipeline, when we have to stall because, for example, we have a memory access, the next instruction, the instruction that is in the ALU, belongs to a different thread. And if it belongs to a different thread, then it doesn't need to stall, right? And probably the next instruction that will belong to the same thread is not yet issued, is not yet executing. And when we issue the instruction, when we start executing this dependent instruction, we have already finished with the memory access. So that's essentially what the fine-grained multithreading means. And this is something that we can find in CPUs, but we can also find in GPUs, as we are going to see. Okay, let's start with the GPUs. They are SIMD engines underneath. That's the first thing to take into account. They are a combination of vector and array processors. But they are special in the sense that they are not programmed in the traditional SIMD programming way with these vector instructions and so on. They are programmed using threads. Such that we can write code for each of these threads individually. But for sure, it doesn't make sense to have like very different programs, for each of these threads. We will likely have the same program for all of them. And that's what we call single program multiple data. Single program multiple data is a programming model, as the name itself means, right? We are going to have a single program that is going to operate on multiple data elements. The way that this program is later executed on the hardware will depend on the hardware, for sure. I could write a single program multiple data program and execute it on a multi-core CPU. But what we are going to discuss here is how to execute this on a SIMD machine, which is a GPU underneath. So that's why first thing to do is to distinguish between what we call the programming model and what we call the execution model, because one thing is the hardware, so the software, and the other thing is the hardware. So programming model refers to how the programmer expresses the code. And there are different ways of doing this. One way is writing a sequential program in C, for example, or in Fortran. You just write a sequential program. Another possibility is to write a data parallel program, for example, using vector instructions, or data flow, or a multi-thread program using OpenMP or pthreads. That's the programming model. And for GPUs, we have CUDA and we have OpenCL, which are the programming model for GPUs. And then the execution model is how do we actually execute this program on the hardware that we have. And this will depend on the actual hardware. Maybe it's an out-of-order processor, maybe it's a vector processor, maybe it's an array processor, maybe it's a data flow processor, etc. So the execution model can be different from the programming model. For example, von Neumann programming model can be implemented on an out-of-order processor. You are familiar with out-of-order processors, right? In out-of-order processors, we don't need to follow the exact sequence of instructions as is defined in the sequential program. But in the sequential program, there is a sequential execution, right? But in the end, the way that these instructions are executed on the hardware depends on the hardware. And for example, in an out-of-order processor, if two instructions that are one after the other are completely independent, they can be issued at the same time or almost at the same time, and they can be executed in parallel. So observe that we are doing concurrent execution, parallel execution, while our program is completely sequential. You understand the difference, right? And in GPUs, what we are going to do is exactly the other way around. We are going to write a program for each of these hundreds, thousands, or millions of threads that we want to run on the GPU, but the way that this program for each of these threads is going to be executed is as if the GPU was a SIMD processor. So we write code for individual threads, and later the hardware is going to collect these threads and put them together in SIMD lanes that are next to each other, and these threads in groups of 32 threads, for example, which is the vector length in NVIDIA GPUs, will execute in parallel. We will see more examples. We will see examples with some detail here. Okay, how can you exploit the parallelism here? Do we have parallelism in this code? Yes, right? We have parallelism in this code. We have a for loop where each of the iterations is independent. So it's something like this. This is scalar sequential code that we are writing there. But now we can see how we are going to execute this on different machines. What happens if our machine is sequential, or if it's data parallel, like a SIMD machine, or if it's multi-thread, like a MIMD or SPMD. So first of all, sequential machine, SISD. So, well, okay, we will execute it like that, right? But depending on what the machine is, indeed, it might be an in-order pipeline processor, or it might be an out-of-order execution processor, right? So if it's an out-of-order execution processor, we can have independent instructions being executed as soon as they are ready, and we don't really need to follow this sequence of instructions that we have written in our program, right? So to some extent, what the out-of-order processor is doing is kind of loop unrolling. The out-of-order processor, for example, could see that this load is completely independent of those two loads, right? So it could issue these instructions at the same time or almost at the same time. And this load and that load and that load might be serviced almost at the same time. Why is that? Because the out-of-order processor operates that way. So it's a way of extracting instruction level parallelism from the code and execute instructions in parallel on the hardware. And we could also, for example, use a superscalar or a VLIW machine as well, right? For example, these instructions here and those instructions here are independent. We could pack them in the same very long instruction word. Okay, that's for SISD. Now for SIMD. Well, the realization here is that each iteration is independent of each other. So if they are independent, we can execute them in parallel, right? We can have something like this. And we can pack these two loads into this one single instruction, which is a vector instruction. And that's our vectorized code. And then these two loads is another vector instruction, and then this to add is a vector add, and then this two is a vector store, right? And we can do that because even though our program was sequential, but we can have, for example, a compiler that detects that these iterations are independent, and then this compiler generates code for a SIMD processor, for a SIMD machine. And the third possibility is that because each iteration is independent, we assign each of the iterations to a different thread. Observe the difference. One thing is talking about lanes in a SIMD machine, another thing is talking about threads in a multi-threaded machine, right? You see the difference, right? The important difference here is in the SIMD machine, if we want the 16 guys or the 32 guys run really at the same time, they really need to be doing exactly the same thing, right? Because it's SIMD, single instruction. But if it's a multi-threaded machine, we have multiple programs, right? We have multiple threads, and each of them could potentially be doing completely different things. But in this example, no. In this example, they are doing exactly the same thing. And this is what we call single program multiple data, meaning that we have multiple threads. These multiple threads are going to run the same program on multiple data. And this is what we do in GPUs. This can be executed on a MIMD machine. This could be executed on a multi-core machine, but we are going to execute this on a SIMD machine, on a GPU. Okay? Yeah. Related concept is this single instruction multiple thread. It's more or less like the same thing. It's more like NVIDIA terminology. So a GPU is a SIMD or SIMD machine, but it's not programmed using SIMD instructions. We just program it using threads, and then we will have the hardware later that will take these threads and put them together in a SIMD unit and execute them all at the same time. So these groups, threads that are grouped together are called a warp, or a wavefront in AMD terminology. At the very end of the presentation, you will find kind of table that I prepared for this terminology, because there is something like this, the official terminology of the lectures, which is, let's say, like vendor agnostic, and then we have the terminology for the different vendors, right? So that's why we included that table at the very end, for you to clarify any possible confusion. Okay, so a warp is essentially a SIMD operation formed by the hardware. So instead of having on a GPU, instead of having one vector instruction for these two loads, what we have is one warp that is going to execute these two loads. or in reality 32 loads at the same time, because a warp consists of 32 threads. But in the end, the way that they execute on the hardware is exactly the same as a SIMD machine, because they share the same PC for all these threads that belong to the same warp. By PC I mean the program counter, right, which is the address of the instruction to be executed, the address in memory of the instruction to be executed. Okay, and then after warp 0 is done with the loads, then warp 1 goes to the next load, and then it goes to the addition, and then it goes to the store. And this is how the program is going to execute. Okay, so graphics processing units are SIMD processors not exposed to the programmer. SIMD versus SIMD, I think that we have already talked about this. You know what is SIMD. SIMD is essentially the same as single program multiple data, as we have already described. And there are two major advantages of this type of machine with respect to conventional SIMD processors, vector or array processors, and are these two things that we are going to discuss separately. So the first thing is each thread can be treated separately. We can execute each thread independently. So it is possible to write code for each thread individually. I told you before, okay, we are going to have one single program for all the threads to operate on the entire amount of data that we have. But if we want to have threads diverging, that's possible as well. I could say in the very beginning of my program, I could write, if you are thread 0, do this. If you are thread 1, do that. That's possible. I can run that program on a GPU, and the GPU internally is just like a SIMD processor. Of course, that's not going to be very efficient, right? Because if you have a SIMD processor and every time that you launch a new instruction, only one of the, you're operating only on a single data element, then you are wasting VLAN -1 lanes, right? And you don't want to do that. But you can do it if you want. So, let's go back to the example here. Assume that a warp consists of 32 threads. So if you have 32,000 iterations and you are going to assign one of these iterations to each thread, you're going to need 1,000 or 1,024, depending on what the K means, warps. Now we are going to have warps executing these instructions, these load instructions. How many warp? 1,000 warps, right? And how are we going to execute these warps? Do we go first all the instructions for warp 0, and then all instructions for warp 1, and then all instructions for warp 2? Can we do that? That could be one possibility, right? But the problem if we do that is that this instruction here is depending on this and depending on this. So we cannot start the execution of this instruction until these two have completed, right? So what do we do in the meantime? What we can do in the meantime is scheduling instructions from different warps. Recall that we have 1,000 warps, right? So we will have to execute each of these 4 instructions 1,000 times for the 1,000 warps, right? So instead of first do all the instructions for warp 0 and then all the instructions for warp 1 and so on, what we can do is interleaving instructions from different warps, because they are completely independent of each other, right? There is no dependence across warps. There is dependence across the instructions of the same warp. So that's what we do. That's why we talk about fine-grained multithreading of warps, and that's why I briefly reminded you what multithreading, fine-grained multithreading means in those slides, that you can take a closer look by yourself. So now, if we have our SIMD units there, or SIMD processor, where we want to execute these warps, we may want to first, issue this instruction for warp 1, and then this instruction for warp 20, obviously if we do this is because we already executed this and this for warp 20, right? Otherwise we could be doing like crazy scheduling, and we really want to schedule things in the right way. So, and after that we might want to, I don't know, schedule this instruction for warp 2 and then this instruction for warp 26. Okay? Okay, so yeah, so this is essentially how the different warps are scheduled onto the SIMD pipeline. So for example, here you see, next one is warp 7. Warp 7, but which instruction? Okay, for example, instruction 0. So we start the execution of instruction 0 for warp 7. And right after that, we say, okay, what instructions are ready? And it turns out that instruction 1 for warp 8 is ready, because the operands are ready, right? And if the operands are ready, that can be the next instructions to the schedule, the next instructions to issue. Make sense? Okay. And here we have a nicer picture of the internals of the GPU, and here you can see this is the SIMD execution unit. We can talk about scalar pipelines, but each of these scalar pipelines is only a SIMD lane, a vector lane. So this is one lane, this is another lane, this is another lane, and thread 0 will execute here, thread 1, thread 2, thread 4, and so on. Okay? This is very simplified. This is a little bit more detail, and you can see the entire pipeline here. This is instruction fetch, decode. Here we have the partition register file, where we have our vector registers, right? And then we have the ALU that can execute addition, multiplication, so on. And then we have a data cache, and then sometimes we will have a miss, right? If we have a miss, what happens? We have to go to the next level of cache, L2. GPUs typically have 2 levels of cache, L1 and L2. So if it's not in L1, you will have to go to L2, which is shared. This is one single SIMD pipeline. You will typically have multiple of these. So each of them has an individual private D cache, but then they have a shared L2 cache. And now you go to L2 and you also miss, so you have to go to DRAM. And now you know how much time this takes, hundreds of cycles, maybe 500 cycles, which is a lot, right? So what can you do in the meantime? Because this memory access was, for example, for warp 1. What can you do in the meantime? Are you going to stall the pipeline and keep this completely idle while you're waiting for the values for warp 1? No, you can execute other instructions, for example, arithmetic instructions, which belong to the execution for other warps, and you can be using the pipeline in the meantime. So those are the benefits of this fine-grained multithreading. With fine-grained multithreading, we are able to tolerate long latencies, for example, like access to memory, because while we are accessing to memory for one warp, we can be executing instructions for other warps. So this is what is called the latency hiding mechanism. It works well, for sure, but it also depends on the workload itself, right? If the workload has a lot of data accesses and very little amount of computation, in the end you will have to wait, right? And that's actually the main bottleneck, I would say, in real GPUs. Okay, you remember this slide, right? Now we don't talk about SIMD vector or array processors. Now we talk about GPUs. And now this add instruction is not a vector add. It's the add instruction for one warp. For example, warp 0. And it turns out that warp 0 is composed by 32 threads. So depending on how many of these functional units do I have, depending on how many of these lanes do I have, I will schedule them. It will schedule the different operations in a different way. If I have one single lane, then I need to first C0, then compute C1, then compute C2, then compute C3, and this is what I would be doing for the 32 threads that belong to this warp. If I have 4 of these lanes, then I can operate on 4 of them at the same time. You also remember this one, right? Now we still call them lanes, and on each of these lanes we run different threads. You see? So we write our code for 1 million threads, and each of these threads has a thread ID, and the values that thread 0 needs to operate on will be here in these registers. The values for thread 1 will be here, and so on. And you also recall this slide, right? We were talking about vector instructions. We don't talk about vector instructions now. We talk about warps. And now our warps contain or are composed by 32 threads, and we want to execute, for example, a load or a multiply or an addition for these 32 threads, but we only have 8 lanes. So the way we schedule the 32 threads of the warp into the 8 lanes is by doing it in 4 cycles. But observe that conceptually it's exactly the same as we have seen for vector processors. Now, instead of talking about vector instructions, we talk about instruction issue for warps. Okay? Any questions here? Okay. So this is like a little bit more of it, right? So how do we distribute the computation here? We have 16 data elements, and for these 16 data elements we are going to to use 16 threads in this case. We assume in this example 4 threads per warp. So what the hardware does, we write our program, right? We write our program with 16 threads, and we tell to each of these threads, you need to operate on this, on this, on that. And then what the hardware will do is say, okay, I have 16 threads, and I'm going to group them in groups of 4, and each of these 4 is going to be a warp. And when we execute the instructions corresponding to these 4 threads, I'm going to launch these instructions for the entire warp at the same time, right? So that's more or less what we have already seen in the past, in the previous slides. So if we want to write GPU code, we will still be using the CPU. We will still be writing serial code, that's for sure. So GPUs essentially are coprocessors. We have GPUs in our laptops, desktop machines, in our cell phones, but we still have a CPU, and that's because we still need it, right? Because there is a lot of workloads that can be run in parallel machines like GPUs, but still there are serial or sequential parts of the code that we need to execute on a regular CPU. So what we do in these cases is we write our program in somehow this way. We will have some serial code that runs on the CPU, and at some point we reach the parallel part of the execution, and what we do is calling the GPU by this is kind of similar to the actual syntax in CUDA. So here what we're essentially doing is calling a function that is going to run on the GPU, and at some point this function will finish the execution, and then we have more sequential code, and then we might have another function. These functions executed in the GPU or device, observe that we call it here device, are called kernels. And for each of these kernels we launch a number of threads. And the way that these threads are organized from the software perspective, from the programmer's perspective, is in blocks. You see? So these are blocks of threads. In total we might have 400 threads, but what we are launching here is, for example, 4 blocks of 100 threads each, right? Observe one thing. This block is a software concept, is independent of the warp. But we will see how do they connect to each other. We're going to see that in the next, in 2 or 3 slides. And this is a very, very simple GPU program, CUDA code. This is the CPU code here. Observe that this is like the element-wise addition. You're pretty familiar with that after yesterday. And here is how do we implement this for a GPU. So what we write is essentially the same as we have there, right? The body of the loop is this addition, and we also have the addition here, right? I mean, the only difference is that, okay, we are separating it in some way, no? So we this is in memory. We go to memory and we store in this variable. This will be stored in a register. Actually, we go to memory, store in a register, and then we go take the contents of the 2 registers, add them, and store in the output position. And observe that these memory accesses are indexed by this TID, and this TID is computed here, is the thread index inside the block index times the dimension of the block. You see, right? Remember in the previous slide I was saying, okay, you are the programmer and you're going to write the program to launch 4 blocks of 100 threads each, right? So this is going to be, you have 100 threads per block. So this is going to be a number between 0 and 99. And then you have 4 blocks, right? So this is going to be a number between 0 and 3. And the size of the block, this block dim, is 100. And this way I can access the 400 elements that these 2 arrays A and B have. This is how we write the program. But observe that the program, these are not vector instructions, right? These are scalar instructions, right? And here in the very beginning I could write, if TID equals 0, do this. If TID equals 1, do that. And I could have completely different programs. I mean, it's actually the same program, it's one single program, but completely different execution path for the different threads. You see the difference already, right? Between CUDA programming and GPU programming. This is a little bit easier, I would say. It's a little easier to write. It's difficult, equally difficult to optimize, that's for sure. Okay, here you have the same thing, but here with a little bit more detail. You can take a look at this by yourself. So this part here is the kernel, is the GPU function, and this part here is the thing that is run on the CPU, because the GPU is a coprocessor. We start the execution on the CPU, and when we reach this kernel call, we call the GPU and execute this onto the GPU. Okay, and now we will be finishing soon, but let's clarify something that is very important here. What's the difference between, or how do relate blocks with warps? Because observe, I started the explanations talking about warps and talking about how these warps relate to the SIMD lanes that we have inside the GPU, right? But after that I started talking about the software, and I said, oh, we are going to write software for threads, and the programmer organizes or arranges these threads into blocks. And now the thing is, okay, if I'm writing code for threads and blocks, how do these map to the warps, right? Well, actually it's quite simple. Essentially, what we do when we write, or what the hardware does when receives the code that needs to execute for a block of threads. This is one so-called streaming multiprocessor in NVIDIA architecture, but essentially for us this is like a SIMD pipeline, okay, or let's call it SIMD compute unit if we want. So when this SIMD pipeline receives the program for one particular block, what it does is dividing the block into warps. So if the programmer said, oh, each of these blocks is going to have 100 threads, what the hardware does is dividing these 100 threads into groups of 32 threads, each of which will be called a warp or a SIMD unit of 32 threads. So now you might be thinking, oh, how do I divide 100 threads in groups of 32? Well, obviously 100 is not a multiple of 32, right? So the last warp will have some unused threads or unused lanes, right? So that's like one of the first hints, programming hints for people who learn to program GPUs is you always use threads that are multiple, you always use blocks with a number of threads that is a multiple of 32, because you really want to use all the lanes for the warps, that are available for each of the warps, right? And you can take a look at the picture here and see how, the different elements that we have inside this streaming multiprocessor. And recall what we were saying before. GPUs are a mix of vector, array processors, and fine-grained multi-threading processors, right? Vector processors, why is that? Because each of these lanes is pipeline, and we can have so I was saying vector, right? So in vector processors we have different types of units. So for example, we have these SPs that execute integer and floating point operations like additions, multiplications, and so on. And here we have these other units that are specialized for load and stores, and then we have this SFU, which means a special function unit that can execute other type of operations, more complex operations like transcendental functions, trigonometric operations, for example. So you see different types of units, but then each of these units might also be able to is also able to execute different instructions. So to some extent they are like array processors and like vector processors. And also they are fine-grained multi-threaded because here we have the warp scheduler and the dispatch unit that are continuously every cycle go into the instruction cache and say, okay, this instruction for warp 0, let's start executing it. This instruction for warp 1, let's start executing it, and so on. Okay? Good. Yeah, so warp-based SIMD versus traditional SIMD. This is just like a comparison between traditional SIMD and warp-based SIMD. I think that we have more or less gone over all of this. You can read the slide more carefully, and also remind you as well what the SPMD means, single procedure or program multiple data. We are writing one single program that is what all these threads are going to run, but each of them are going to operate on different data elements. At some point they can also synchronize. This is something that we will probably talk about when we continue with GPU programming. And yeah, essentially multiple instruction streams that execute the same program and operate on different data. And the second thing, just very, very briefly before we finish, is another advantage of the SIMD architecture is that we can group, or at least potentially we could group threads into warps flexibly. This is something more, it's more like a research proposal rather than an actual implementation on real hardware. But it comes from a very reasonable concern, which is that you don't want to, you in principle want to avoid, you already know why, you want to avoid, like, separate different control flow paths for each of the different threads. Even though you can write that, you can write your program in that way, but you in principle want to avoid that. And why is that? Because in the end they are only like SIMD pipelines, and when you reach a divergence point like here, this is a branch and some of the threads are going to be through path A, others through path B, and when this happens, what will happen is that you are issuing instructions for the same warp twice, right? Instructions for path A, instructions for path B. How do you really implement this? It's a SIMD machine, it's a SIMD, it's a vector or array processor, right? So it has a mask. So in your mask, when going through path A, this is 1 0 1 1 0 0 0 1, and then you complement and execute path B, and then this is 0 1 0 0 1 1 1 0 in the vector mask, right? Problem with this, I mean, the good thing is that it works. The bad thing is that we are wasting some of the lanes, right? So we are not exploiting all the throughput that the GPU can give us. Okay, so what was proposed by some paper, you will see the title of the paper somewhere, is to dynamically merge threads such that we have threads that were originally going to belong to different warps, but the hardware says, oh, I have divergence here. I have some threads here that are not going to execute, but I also have another warp that has some threads that can merge with the other ones, right? Could execute at the same time. So what you do is that you compose, what the hardware, the warp scheduler does is that composes like a artificial warp in this case, and you see that this warp Z contains threads that originally belong to warp X and warp W, and this way you can have a more efficient execution. That's you have a nice example here. That this is the title of the paper: Dynamic Warp Formation and Scheduling for Efficient GPU Control Flow. And here you can see a very nice example, pretty simple as well. And this is another example. We might assign you this for reading. You will have a chance to read this in detail, but let me very briefly introduce. We have already mentioned like two main bottlenecks in GPUs. One of these is the divergence that we have just discussed. The other thing is the access to memory, for example, very low latency operations. And in this paper, they try to deal with both. So with respect to, so this is like the typical default scheduling that we have in GPUs is round robin. So you first schedule instruction for warp 0, then for warp 1, then for warp 2, and so on. And even though you can achieve some latency hiding, not so much if you see this timeline. Here, all threads, all warps start computing arithmetic operations, and at some point they need to access memory, and this takes a lot of time, a lot of cycles, right? And you cannot resume the computation inside the pipeline until you have obtained all the data from DRAM. And yeah, of course, there is some latency hiding here, right? Because we are somehow overlapping a little bit of computation with a little bit of data access, but not that much. Why is that? Because there are many accesses to memory here. So this is, I mean, it's the main bottleneck. So what in this paper they propose is to have like larger warps and then schedule like kind of sub warps that are dynamically formed. For example, this is the entire warp, this is the mask, and instead of scheduling these 4 and then these 4, what we do is ignoring those for which the mask is 0, and we only schedule those for which the mask is 1. So if we do that, I mean, this is for this is the way of reducing. No, this is for branch divergence. It's not for the memory access, but you see more or less how it works. It's kind of similar to the previous technique. And for the long latency operations that we do is like a 2-level warp scheduling. They organize the warps into smaller groups, such that they first schedule round robin inside a group and then schedule round robin across groups. And this way, as you can see, it's quite clear. You can achieve more overlapping, right, than there. You can achieve more overlapping and save execution cycles in the end. And this is the paper. And because it's more than 4 p.m., I think that we are going to finish here. There are a few more slides. Probably if I have the chance to give you a GPU programming lecture another day, we will probably start with these ones very quickly. Let me know if there are any other questions or maybe we can finish and ask questions in Moodle or whenever you want. Okay? Thank you very much for your attention.